In the third part of the additional practice problems, we see some problems about properties of polynomials. In this case, we're just looking for intercepts and then what the behavior of the graph is at each of the x-intercepts. So this is pretty straightforward. The y-intercept, as usual, comes from plugging 0 in for x. So we can do that without multiplying this thing out. Put 0 in for x, this looks like negative 1 squared times 1 times negative 1 squared, so that's positive 1. So therefore, the point 0, 1 is the y-intercept. To find the x-intercepts, we set the formula for the polynomial equal to 0 and solve for x. We know that a product can only be 0 if any of the factors are 0. So either x minus 1 has to be 0, or x plus 1 has to be 0, or 3x minus 1 equals 0, which tell us that our x-intercepts are at 1, 0, negative 1, 0, and 1/3, 0. Now, as far as the actual behavior at those points, that just depends on the multiplicity of the factor in the original polynomial. So the factor that gave us this guy has multiplicity 2, and so that means that our graph just touches the x-axis at that intercept. The factor that gave us this x-intercept is this guy, which has a power of 1, right? There's no power there at all. It's a power of 1, which is odd. And so the graph cuts through there. And I actually know the special case that if that multiplicity is 1, then it cuts through, waffle or think about it, it just goes straight through. And then finally, the factor that gives us the x-intercept 1/3, 0, has multiplicity 2, which again is even. And so, again, that will just the graph. I encourage you to try graphing this just to see. You will have to set your y, the scale in the y direction to be something fairly small in order to be able to see what's happening at the x-axis, because this function will get very, very big everywhere else. But if you can zoom in enough at these points, you should see that is indeed what's happening. So those are our 4 different intercepts and the behavior at each of the x-intercepts. So, same deal here. The y-intercept is going to come from g of 0, which in this case is 0. So that means that 0, 0 is the y-intercept, but of course 0, 0 is also on the x-axis, so that's also an x-intercept. To find all of the x-intercepts, I just set the formula for the function equal to 0 and solve, and I'll have 0, 3, or negative 3, which means that my x-intercepts are 0, 0, 3, 0, and negative 3, 0. The multiplicity of all of these factors is 1. Everyone has a multiplicity of 1, which is odd, and so these all cut through. None of them just touches the axis. And then the third one, we see that our y-intercept is going to happen at h of 0, which is 1/3 times negative 3 squared times 1 cubed, and so that's 1/3 of 9, which is 3, so therefore 0, 3 is the y-intercept. To find the x-intercepts, I'm setting this equal to 0, which means that either x is 3 or x is negative 1/2, and so my x-intercepts are 3, 0, and negative 1/2, 0, and the multiplicity of the factor that gave us this guy is 2, so the graph just touches there, and the factor that gave us this x-intercept has multiplicity 3, which is odd, and so this crosses, And this crosses in that sort of weird, sort of waffling way that we talked about, where you kind of come up and think about turning over and then don't and keep going up like that. So so it's kind of a special case of crossing, but nevertheless, that does cross the x-axis, does not just touch it. And so that's pretty much it for polynomials. I hope you recognize that a lot of what we're doing here is similar to what happens with quadratic functions if we happen to have them in a factored form originally. And so hopefully there you can see the connection between 4.3 and 5.1, those kinds of problems.